This video is about alternative cementitious materials. These are cements that are a little bit different than Portland cement. I'm going to tell you about types of ACMs, some fun facts about them, and ultimately where I think they can best be used. My name is Tyler Lay, and I am obsessed with concrete. Usually, when we make concrete, the ingredients are pretty simple: rock, sand, cement, and water. And when we say cement, we mean Portland cement. But when we make concrete with ACMs, we use a different cement. That's the only difference. The rocks are the same, sand's the same, water's the same. Now the admixtures can be somewhat different. ACMs have different chemistries though, different properties, and we don't understand them as well. But they have been used as repair materials for decades because usually they get strength really fast. However, one other benefit of ACMs is that they can sometimes have a lower carbon footprint or lowered amount of embodied energy. There's three main types or categories of ACMs. There's clinkered, calcined, and non-clinker. And what that means, what the differences are the amount of heat needed to be put into the production. Something that's clinkered has high amounts of heat. Something that's calcined has middle amounts, and something that's non-clinker is stuff that you find around, like fly ash or something you dig up and you add an activator to it. Now, you don't get something for nothing. Things that require low amounts of heat usually require high amounts of energy in their activator, in their water, in their whatever liquid you mix with them. Ultimately, I think a good analogy to compare ACMs to OPC is like Coke and the other types of Cokes. They're all Cokes, but they're all a little bit different. For example, Coke Zero, it's got 0 calories, and they say it tastes like Coca-Cola. I think it's a little bit different. Then there's Diet Coke, very, very, very different. And then there's Coke Life. This is the new kind of hippie Coke, right? Start with some fun facts. Calcium aluminate cements, they are extremely fast-setting cements, but the microstructure that they produce isn't stable. You're actually going to see the material lose strength after about 60 days. How much strength? Sometimes 50% of the strength. And that scares people. But what you have to do is over-design. If you need 4,000 PSI, then that means you need 8,000 PSI in the first 7 days, because long-term you're going to be back at about 4,000 PSI. These cements were widely used to repair runways during World War II. So if someone bombed a runway, they would patch it with calcium aluminate cements. They'd be able to land planes and fly planes off it very, very rapidly. And who cares if they left it in place? Because it's going to degrade over time. Calcium sulfoaluminate cements, they are extremely fast setting. They're like wild stallions if you're not careful. Super fast strength gain, and magic things can happen if you combine them with latex or other polymers like that. Alkali activated, or also known as geopolymers. They are 100% fly ash and slag plus activator. The problem is you can't use just any fly ash, or you can't just use any slag. You need the right materials, and you have to tailor that to the right activator. And a lot of that's still being studied right now. And the properties are extremely dependent on the materials used to make them. This plot shows some of the different ACMs on the bottom versus the emissions, or the amount of energy made to produce them. The blue bars is the energy that's used in the clinkering process. The yellow bars is the energy that's used in the activator, or the production of the material. So you can see Portland cement is the highest. It has the highest carbon footprint of all of them. Some of them, like a calcium sulfoaluminate cement, have about 50% of the amount of energy needed to produce it. And you can see they all fall in different places. Here's the compressive strength. Notice I'm showing 1 day, 3 days, 7, 28, and in black is OPC. And the other ACMs all are different. Some start out a little bit lower than Portland cement. Some are much higher after 1 day. For example, these have about double the strength of Portland cement. So strength is great, But what about durability? Oh man, what a question. I'm going to summarize some of the findings that we've had from a big research project sponsored by FHWA, or the U.S. Department of Transportation. The project was led by Georgia Tech. Oklahoma State was involved, Turney Consulting, and so was the U.S. Army Corps of Engineers. We found for calcium aluminate cement, some of the pros is that they have very, very low amounts of ion penetration and low amounts of shrinkage. That's good for cracking. Some of the cons, they lose strength over time. As this reversion happens, it can cause cracking. And they also have poor scaling performance in freeze-thaw. So where should these materials be used? I think a good application would be tropical environments or very, very dry climates. And where should they not be used? Anywhere where you're worried about freeze-thaw environments. Calcium sulfoaluminates, they have a lot of pros. Low amounts of shrinkage, very, very low. High amounts of strength gain, and they have great freeze-thaw performance if you use a polymer at a 0.35 water cement ratio or a low enough water cement ratio. Some of the cons, they show pretty high ion penetration. So where should it be used? Pavements and freeze-thaw environments, great application as long as you use the polymers plus some type of low water cement ratio. Dry climates, great application for them. Where should they not be used? Places where you want to protect reinforcing steel. We see that that hasn't been a great performer for these materials. Alkali activated. Some of the pros, they have a low carbon footprint, they have low shrinkage. The cons, they have poor scaling performance, poor freeze thaw, and high amounts of ion penetration. So where should they be used? If you have dry climates, this is a great application for them. They shouldn't be used in freeze thaw environments or places where you want to protect reinforcing steel from salts. Be careful though. We used one type of alkali activated material. That doesn't mean they're all the same. So what does this mean? ACMs are not the best to be used in all environments, but they have outstanding advantages in certain locations and situations. And ACMs are tools. I used an analogy earlier comparing them to Coca-Cola Classic. I think maybe a better analogy, OPC is a Swiss Army knife. It can be used anywhere. But sometimes, if I want to screw in a bolt or a screw or something, I don't necessarily need or want to use a Swiss Army knife. I may just go get a screwdriver. That's what ACMs are like. If I'm going to be doing a lot of something, especially something where I want outstanding performance, then I'm going to seek them out. They are useful tools to help make our industry better. So look into the future. I think we're going to see blends of OPCs and ACMs in the future. I think they're going to become regular things that we do every single day. I think if you're interested in decreasing shrinkage, improving ASR performance, or decreasing ion penetration, I think these materials have outstanding possibilities. Hey, I think I need your help. We need to document outstanding cases of these ACMs. If you've got a case study, something that you know a structure that's been in place for about 20 years, and we need to know information. We need to know about the mix design, the type of materials, what was done, as much information as you can. That would be outstanding. We may even want to get a core from you so that we can analyze the material and see how it's performing. Thank you so much for watching this video. Please give me a thumbs up, share this video with somebody else. Tell me, what are your thoughts? What are your concerns about ACMs? And don't forget to subscribe. Take care. Bye.